I'm going to talk about two-dimensional Coulomb's law problems. I'll assume that you know what Coulomb's law is. I'll also assume that you know how to work with vectors. All right? So give me a minute to make a picture. All right, so I've drawn a picture that denotes four charged objects sitting on the vertices of a square with sides of length 2.5 centimeters. Okay, the side length is denoted by L. The four objects are denoted by the letters A, B, C, and D. The charges on each of the objects is denoted by a variable formed from the letter Q and a subscript which is equal to the letter denoting the corresponding object. So Q sub A, Q sub B, Q sub C, Q sub D. And Q sub A is equal to plus 3 microcoulombs, Q sub B is equal to minus 3 microcoulombs, Q sub C is equal to plus 3 microcoulombs, and Q sub D is equal to minus 3 microcoulombs. What I'd like to do is I'd like to find the force, the total electric force on object B. Okay, so we're going to have a contribution from objects A, C, and D. 3 force contributions. We have to find the vector component representation of each of those 3 contributions. Then we will do a vector sum to get the total electric force on object B. Okay? Let me now draw some arrows to represent each of those electric force contributions. Between B and C, we have an attractive force, so I'm going to draw an arrow down. Between B and D, we have a repulsive force, so I'm going to draw an arrow away from object D. Between B and A, we have an attractive force, so I'll draw an arrow to the left. Okay? And let's denote the force with respect to objects B and C by the vector F sub BC. Let's denote the force with respect to objects B and D by F sub BD. And let's denote the force with respect to objects B and A by F sub BA. All right, and so we need to find the component representation of each of those forces. Now, I'm going to be using the following coordinate axes, following coordinate plane. Okay, so the horizontal axes I'll denote by X axis, the vertical axis I'll denote by Y, and I'll be using the Coulomb's law formula, which is equal to K times Q1 times Q2 divided by D12 squared, which where K is the electric force constant, Q1 and Q2 are the net charges of two objects for which I'm calculating the electric force, and the distance between those two objects is denoted by D sub 1, 2. And K, the electric force constant, is equal to 9 billion Newton meter squared per Coulomb squared. Okay? All right, so now let's calculate the forces. So F B A is going to be a vector with a negative x component and a 0 y component. So that is equal to K times the absolute value of QA QB divided by L squared, and let me remember to put a minus in front, comma 0. Right? So I used Coulomb's law to find the magnitude, and then I put a negative in front because I had a negative x component. Now, F sub B C, that one is going to be a vector with no x component and a negative y component. Minus K times the absolute value of QB times QC all over L squared, and F sub BD, that has a non-zero x and y component. Both the x and y components are positive, and we need to use trig functions to calculate the x and y components. So the x component is going to be, let me write the magnitude outside of the vector. K times Q sub B, the absolute value of the product of Q sub B and Q sub D, divided by, and what's the distance between the corners of the square? Using the Pythagorean theorem, you can determine that it's L root 2. Okay, so that's the magnitude of the vector. So to get the x component, I would multiply that magnitude by the cosine of 45 degrees. To get the y component, I would multiply that magnitude by the sine of 45 degrees. Now we need to add the vectors together. Notice that the absolute value of all of the charges is the same. Notice also that there's a lot of commonality in the components of the different vectors. Let me represent the following quantity by the Greek letter gamma. Gamma is equal to K times QA squared over L squared. So notice that by doing that, I can write F sub BA as minus gamma comma 0. All right, because again, the product of QA and QB, the absolute value of that is equal to the square of QA, because all the charges have the same absolute value. F sub BC, that's equal to 0 comma minus gamma. And then let's simplify F sub BD. So would you agree that the cosine of 45 degrees is root 2 over 2? And same for the sine of 45 degrees? Would you also agree that if I square the root 2, I get a 2? So apparently that vector is equal to, let's see, gamma times root 2 over 4, comma, gamma times root 2 over 4. Okay, so putting it all together, the sum of those vectors, so F total, is equal to, and then if I sum the x components, I get gamma root 2 over 4 plus 0 minus gamma, and then gamma root 2 over 4 minus gamma plus 0. And there you have it. So you can now use your calculator to determine the value of gamma. Gamma is 9 times 10 to the 9 times 3 times 10 to the minus 6 squared, all over 2.5 times 10 to the minus 2 squared. And then plugging that into the formula, you'll get the components. And you can find the magnitude of the total force vector by taking the sum of the squares of the components and then taking the square root of that. So doing that, you will get 118 newtons towards object D. Okay, so that's the magnitude of the force, and it'll be down and to the left. Okay? Now I would like you to do an example. Give me a minute to make a picture. Okay, so my picture denotes 3 charged objects lying on the vertices of an equilateral triangle. The sides of the equilateral triangle all have a length of 2 centimeters. The measures of all the angles are 60 degrees. The objects are denoted by the letters A, B, and C. The charge on object A, Q sub A, is equal to minus 2 nanocoulombs. The charge on object B, Q sub B, is equal to plus 1 nanocoulombs. And the charge on object C, Q sub C, is equal to plus 1 nanocoulombs. Now, I would like you to do the following. Find the magnitude and direction of the total electric force on object A. Okay? So pause the video and work that out now, if you like. Okay, so I'll go ahead and work it out as well. So between A and B, there's an attractive force. So I'm going to draw an arrow towards B. Between A and C, there's also an attractive force, so I'm going to draw an arrow towards C. And let me denote the force contribution from object B as F sub AB, and let me denote the force contribution from object C as F sub AC. And so we need to find the components of those two vectors and then find the vector sum and take it from there, right? So I will be using the following coordinate axes to specify the vector components. The horizontal axis I'll refer to as x. The vertical axis I'll refer to as the y-axis. Okay? And we know that I can, because it's an equilateral triangle, I can draw an altitude, which is also an angle bisector. So I can form right triangles, and so now the 60-degree angle with respect to object A, I've bisected it, so now I have two 30-degree angles. All right, so F sub AB, let's determine that one. So let's first find the magnitude of the vector. So K times the absolute value of Q sub A times Q sub B divided by D squared. And then to get the X component, I need to multiply that magnitude by what? By the sine of 30 degrees. And that'll give us a positive component, which is what we need. What about the Y component? The Y component will be negative, and we will want to use minus cosine of 30 degrees for that part. Okay? Now, let's now do F sub AC. So let's first find the magnitude again. So K times the absolute value of Q sub A times Q sub C divided by D squared. And to get the X component, I need the sine of 30 degrees again, but this time I'm going to have a negative X component, so I'll use minus sine of 30 degrees. And for the Y component, it'll be negative, and I'll need to use the cosine of 30 degrees. Okay? When I add those vectors, notice that the sum of the X components will add to 0. Okay? Also, if I put the negative sign on the Y component, the last Y component, notice that the Y components of both vectors are the same. All right, so F total will equal K times, and by the way, notice that the products QA times QB and QA times QC are the same. So that'll simplify the representation of the total vector. Zero comma minus 2 times the cosine of 30 degrees. Okay, and so the absolute value of the Y component will give the magnitude, and the direction will be downward, directly downward, because the X components cancel. Okay, so let's go ahead and calculate the magnitude then of this vector. So 9 times 10 to the 9 times QA, the absolute value, so 2 times 10 to the minus 9, and QB, 1 times 10 to the minus 9, divided by d squared, so 2 times 10 to the minus 2 squared, and 2 times cosine of 30 degrees, 2 times, and the cosine of 30 is root 3 over 2. Okay, so you can put this in your calculator, or you can play with it first, simplify. So you see that some of the powers, the 10 to the minus 9 and the 10 to the 9 cancel. And okay, so eventually you have to put it into your calculator, and so you will get 7.8 times 10 to the minus 5 newtons, and that will be damn.